Okay, for the next module, we're going to talk about atomic spectroscopy. So this still deals with the interaction of matter with light, but we're going to look at this interaction at the atomic level. Okay, so far yung UVPs that we have discussed, that's molecular spectroscopy. Okay, so we're going to talk about the spectroscopy at atomic level. So when we're talking about atomic spectroscopy, okay, when we talk about the quantum theory, the atoms, molecules, and ions, they have only a limited number of discrete energy levels. Okay, so in this quantum theory, whenever energy is absorbed, okay, some of the particles go to a much higher energy level. So for the absorption of radiation to occur, the energy of the exciting photon must exactly match the energy difference between the ground state and one of the excited state of the absorbing species. Okay, so electromagnetic radiation is produced when the excited particles relax to lower energy levels by giving up their excess energy as photons. So we all know the one with higher energy level, they are usually what? Unstable. The excited state is an unstable state. So most of the time, the tendency whenever you have a material that is an excited state, it will go back to the ground state. And in doing so, it will emit, okay, the excess energy. So the term that they use there is emission. Now, atomic spectroscopy is usually based on the breakdown of the sample into atoms, followed by the measurement of the atom's absorption or emission of light. So if you're going to look at atomic spectroscopy, okay, unlike the one that we have in UVPs, where the absorption is by molecules and the emission is also by the molecules, here it's mostly on the atomic level. So the atoms is excited, or when they absorb energy, they are excited. Okay, being an unstable state, it will emit back the light. So if we're going to look at this, okay, atomic spectroscopy deals with the absorbance, fluorescence, or emission or luminescence of atoms or elemental ions rather than molecules. So one thing that separates the atomic spectroscopy from the typical molecular spectroscopy is you need this process of atomization. So this is just the process of converting sample to gaseous atoms or elementary ions. So this can be done in the sample chamber or the sample holder. Okay. So if you're going to look at the optical components that we have discussed from the previous module 4.2, you will see that the AAS usually has a different black diagram compared to the other spectroscopic methods. Now, what information we can get from atomic spectroscopy? It provides information on the elemental composition of sample or compound. Okay. Now, all molecular spectroscopy, UVBs, IR, Raman, they give molecular function group formation, but there's no elemental information. So that's the difference of this atomic spectroscopy. So it is at the elemental level, because it's look at the atom, unlike the molecular spectroscopy that has been discussed already. Now, the basic process of atomic spectroscopy is the same as in the UVBs, fluorescence, okay, that was mentioned for molecules. So you can have what we call light interacting with your sample. So this is an atomic level. So there's what we call the absorbance or the absorption of the energy, forcing the atom to go from lower to higher energy level. And then you can also look at it with respect to fluorescence, where when light interacts with the matter, it gets excited, and being in the excited state, it can go back, okay, relax to a lower energy level, and in giving so, it will emit light or energy in the form of light. Now, if we're going to look at the difference of atomic spectroscopy from molecular spectroscopy, you don't have vibrational level. So that means, okay, this leads to much sharper absorbance, fluorescence, or emission bands. So if we're going to look at the position of the atomic bands, they are well defined, and characteristics of a given element. So each element has their particular line spectra where you observe peak at a certain wavelength. Okay, so qualitative analysis, we could say, is easier in atomic spectroscopy than in molecular spectroscopy. So all you need to know is the signature peak of each element. What are, or where can you find the line spectra of a particular element? So once you match them up, you can make sure that is made up of that element. Okay, and if you're going to look at the atomic spectra, when atoms are usually excited, they emit light of certain wavelengths, which corresponds to these different colors or line or atomic spectra. So these are their signature peaks. Now, each element produces a unique set of spectral lines. And since there's no elements emit the same spectral lines, elements can be identified by their line spectrum. So they have a unique signature peak. So no two elements would have the same line spectra. Now, you may ask, what causes these spectral lines? Okay, so most of the spectral lines as emitted by a single atom, they are associated with the changes in the energy of its orbiting orbital or electrons. So as the atom gains energy when heated, their electrons eventually release the extra energy in the form of visible light. Now, the light would exhibit unique frequency or spectral lines, characteristics of this energy change. Okay, so if you're going to look at this energy level diagram, you can consider that the outer electrons of this what we call element, and they describe the atomic spectroscopy process. So every element is a unique set of atomic orbitals. The P, the D, and the F split, okay, by spin or beam coating. Then you can look at the spin quantum number and the orbital motion. It creates a magnetic field that perturb each other, okay, or a couple. So if parallel, you're going to have higher energy. If anti-parallel, you're going to have a lower energy. So if you're going to look as the number of electrons increases, the number of the levels also increases. So some of the examples of more complex emission spectra, you have lithium. It has 30 lines, okay? You have cesium that has 645 lines, and you have chromium that has 227 lines, okay? So in atomic spectra, when we're talking about atomic spectra, we could say it involves a discrete energy transfer, okay? So since the electrons are only able to give a specific amounts of energy, the energy difference between two allowed energy levels, the electron will just only be able to give of specific frequencies of light, those corresponding to transitions between allowed energy levels. And if you're going to look at this, you can measure the separations in terms of electron volts. 1 electron volts is 1.602 times 10 to the negative 19 joules, or around 96,484 kilojoules per mole. Now, specifically, if you look at the resonance lines in sodium, it results in the transition between an excited electronic state and the ground state. And if you're going to look at the other lines here, okay, it occurs at 330.2, 330.3 nanometer, as well as at 285.30 and 285.28. Okay, so if we're going to look another example, we can look at the atomic magnesium. So there are two 1s electrons, and these are excited singlet and triplet with different energy. So you have here the singlet and the triplet. Oh, they found out there's a similar pattern between the atoms, but there's a different spacing. And the spectrum of ion, okay, so when we're talking about ion, magnesium 2+, it's different from just magnesium. Okay, so if we're going to look at the effect of the temperature on the atomic spectra, Boltzmann equation can be utilized here. Okay, temperature changes the number of atoms in ground and excited state, and temperature has to be controlled. So if you're going to look at the Boltzmann equation, so you have here the number of atoms in excited and ground state respectively. And then you have K. T as the temperature, K is the Boltzmann constant. Delta E, that's the energy difference between the ground and excited states. And then you have T as the temperature, and then P1 and P2, they are the number of states having equal energy at each quantum level. So there's an exercise of this one that we're going to talk during the asynchronous session. But the thing that we want to know is how is the effect of temperature on atomic spectra. So if we're going to look at varying the temperature by 10 Kelvin, it hardly affects the ground state population, and it not noticeably change the signal in atomic absorption, because the excited state population changes by 4% when the temperature raises 10 Kelvin. Emissions density only rises by 4%. Now, atomic absorption is not as sensitive to temperature as atomic emission, which is exponentially sensitive to the temperature. And we can also say the emission is usually carried out with ICP, inductively coupled plasma, whose temperature is more stable than the flame. So as we could say here, the atomic absorption is not as sensitive to temperature as atomic emission, which is exponentially sensitive to temperature. And the emission is usually carried out with ICP, or inductively coupled plasma, whose temperature is more stable than the flame. Now, if we're going to look at the types of the atomic spectroscopy, so there are 5 types of atomic spectroscopy. So the one that will be covered in 137 would be 3 of them. We have the atomic absorption spectrometry, which is the AAS, the atomic emission spectrometry. This involves, we could say, the flame atomic emission spectroscopy, which is FAES, and the inductively coupled atomic emission spectrometry, or ICP-AES. We also have atomic fluorescence spectrometry, which is not going to be covered in this course. And then we have the atomic mass spectroscopy, a spectrometry, which is of many types, but we're just going to cover the ICP, the inductive coupled plasma mass spectrometer. So the rest of this atomic mass spectrometry, you have the thermal ionization mass spectrometry, secondary ion mass spectrometry, and laser microprobe mass spectrometry. And then we also have this atomic X-ray spectrometry, which is absorption, fluorescence, and the emission form. Okay, so I would suggest that find time to watch the videos. So these videos usually discuss the double beam AAS, and it gives you an overview of the segment of the equipment, although we have some intro of this from the previous module. The mechanism inside, the monochromator, and an analog readout. Okay. Now, let's talk about AAS. This is, I would say, the most popular atomic spectrometry. Now, my only experience in atomic spectroscopy is AAS. Okay. Now, in atomic absorption spectrometry, or AAS, the light of a wavelength characteristic of the element of interest is shown through the atomic waveform. So some of this light is then absorbed by the atoms of that element. Now, the amount of light that is absorbed by this atom is then measured and used to determine the concentration of that element in the sample. Okay, so the way that you're going to look at here, the light that is absorbed by the atoms, that's the one that is going to be measured. So if you go, the way that you look at this, so the light or energy in the form of light was absorbed by the atoms, and then, okay, these atoms that was that absorbed the light, that is being measured, and it is correlated with the concentration of that element. So the more light that you have, the more atoms that's going to absorb the light. So the higher will be the concentration that you have there. Now, sometimes if you have too much light, but all of the atoms has already what we call absorb that light, so the signal that you have is just limited by the amount of the atoms that you have. Now, AES, or atomic emission spectrometry, also known as the optical emission spectrometry. So the way that it works, the sample is subjected to temperatures high enough to cause dissociation into atoms. So here, you're looking at the emission. So that means you need to have a situation or a condition wherein you're going to excite, okay, your atoms, and then they're going to dissociate. Okay, so the temperature that you use is really high enough, cause dissociation into atoms and collisional excitation or ionization of the sample atoms that takes place. So once these atoms or ions are already in the excited states, they can decay to lower states. And in doing so, that's where emission takes place. So the transition from the higher energy level to the lower energy level, or from the higher states to the lower states, okay, that's where radiative energy transition happens, or emission takes place. Now, the intensity of the light emitted, okay, at specific wavelength is measured and used to determine the concentration of the elements of interest. Maybe between the two, this has a high energetic requirement because you need a high temperature. Now, the other one, which is the atomic fluorescence spectrometry, okay? So this is similar to fluorescence in molecular spectroscopy. So there's an absorption that you have there, and then, okay, when your sample goes back to a lower energy level, it can have non-radiative transition. So the way that you're going to look at this, you have a light source that excites the atoms only of the elements of interest to radiative absorption transition. Now, when these selectively excited atoms decay through a radiative transition to lower energy, their emission is determined or measured to determine the concentration. Now, the selective excitation of the AFS technique can lead to low or fewer spectral interferences than in OES. Okay, and you use several excitation sources and detectors that can be used at one time. And another, we could say, difference of this compared to the previous one, and I would say similar to fluorescence, is the detector that is attached is viewed at 90-degree angle, which prevent the incident light from polluting the detected fluorescent light. So it's not a straight one. So it's just like you excite them and then you look 90 degrees at what will happen. So this is typically a fluorescence phenomenon. Okay. Now, the atomic mass spectrometry is, I'm not sure if you're familiar with the concept of mass spec or mass spectrometry, which we're going to discuss after this module. So mass spec usually measures the number of singly charged ions from the elemental species within a sample. Now, the mass spec does not measure absorption, emission, or fluorescence of radiation from high temperature sources such as flame or plasma. Okay. Now, a quadruple mass spectrometer separates the ions of various elements according to their mass spec. Now, similar to the function of the monochromator in the emission and absorption spectrometry, it separates light according to wavelength. So you have here a quadruple mass spectrometer. It separates the ions of various elements according to the mass to charge. So this works really like a mass spec, but at the atomic level. Now, if you're going to look at the block diagram of the AAS, this is how it looks like. You have a light source, usually in the form of a flame, or you can also have a graphite furnace. And then, no, the light source is just what we call the xenon arc lamp. It's not a flame. The flame that you have there is where when you put the sample. Okay, so the sample whole, it's not really a sample order. It's just like a hose siphon the thing, but it is really like a nebulizer. I'm not sure if you're familiar with a nebulizer. If you're asthmatic, okay, you use that thing. So what you do when the sample is introduced, it's nebulized. So it's easy for it when it goes to the flame to change into ions or separate, okay, the atoms. Then you have a monochromator. That's where you put a narrow wavelength where you can select. So usually each of these elements, they have their own wavelength because of the line spectra concept. And then you have a detector, and from the detector you have a readout system. So if you have what we call an AAS, the light source that you can have, it should be of narrow bandwidth for light output. So the atomic absorption lines are remarkably narrow, 0.002 to 0.005 nanometer. Okay, and a separate light source and filter is usually used for each element. So commonly you use what we call a discrete light sources, such as the hollow cathode lamp, or a monochromatic one like a laser. Okay, so we discussed some sort of this in the optical parts of components of optical instruments. So if we're going to look at how hollow cathode lamp works, you have a high potential around 300 volts applied across the electrodes, results in ionization, inert gas. Okay, and then what happened there? The 300 volts, it converts the argon to argon plus, and then after that, okay, the positive ion would strike the cathodes and hits the surface. So what happened when it hits the surface? Some of the element, usually the metal there, is excited and dislodged in gas phase, the so-called sputtering. And then the excited elements relaxes to ground state and emits the characteristic radiation. I think there's a much better explanation in the previous module for this. Okay. Now, maybe in our synchronous meeting, we can answer the question on this about laser. Okay. I think it's much better being done during synchronous meeting. Now, if you're going to look at the instrumentation for the AAS, it uses the same single beam or double beam optics described earlier for molecular absorption spectrometer. However, okay, the main difference that they have there is this so-called atomization process. The analyte must be converted into the atom. So usually it's in the form of that nebulizer that I have mentioned. So the analyte is in the solution form. If the analyte is the solid, then you have to bring the analyte into solution before analysis. So if you're going to look at the atomization process, so as I've told here, you have what? A solution. And then you put in the nebulizer. So you have a sprayer, okay? And then you have desolvation. So there's a solid gas aerosol, okay? And then the volatilization, forming gaseous molecules, and then dissociation, all of this happening while it is in the flame, okay? And then you form an atoms and the atomic ions. So you can excite them. So you have an excited ions, excited atoms, and excited molecules. And each of them will give their respective energy. Okay? So the process of converting an analyte to a pre-gaseous atom is atomization. So converting an aqueous analyte into a pre-atom, it requires that we strip away the solvent, volatilize the analyte, and if necessary, dissociate the analyte into pre-atoms. And the way that you're going to do it is either flame ionization or electrochemical atomization. Lately, they have this what we call inductly coupled plasma. Okay. So if we're going to look at this is even two, this should be three. Okay. So if we're going to look at these three atomization method, this table summarizes it. So look at the temperature that you have there. The inductively coupled plasma is just way too high. Almost how many times? 3 times? Or 2 to 3 times? Okay. Higher temperature than the flame and the electrothermal or graphite furnace. And the type of spectroscopy that we have here, the ICP, we only have emission and mass spectrometry. In the flame, you have absorption, emission, and fluorescence. In the electrothermal or graphite furnace, you have the absorption and fluorescence. Now, if you're going to attach what is the method that you have here, so if it's emission is ICP-OES. If it's mass spec, it's ICP-MS. If it's in the flame, you have the flame atomic absorption spectroscopy, or FAAS. And if it's emission, it is an AES. And if it's a fluorescence, it's an AFS. Okay. Now for the graphite furnace, they have a term for absorption is electrothermal AAS. If it's a fluorescence, it's electrothermal AFS. So we're talking about atomization method here. So let's look at the step. So nebulization is the first step. So that's where you introduce your sample. So the solution sample, get into fine droplets by spraying through the thin nozzle or passing through a vibrating crystal. So once there's nebulization, the next thing that you have is desolvation. So what is desolvation? Dissolve. You're removing the solvent. So heat droplets to evaporate of the solvent, just leaving analyte and other matrix compound. So you nebulize, you put them in, make them into a fine droplet, and then dissolve, you remove the solvent. And then there's no more solvent, only the matrix substances there in your sample. The next thing that you're going to do is you undergo volatilization or vaporization. So you convert solid analyte or matrix particle into gas. And then you could have also dissociation and atomization. So this is you break up your molecules into gas, phase, into atom. And then you have ionization. It causes the atoms to become charged because you have an ions. And then you have excitation. So with light, heat, and other things, you use this for spectra measurement. Okay. So let's go on the atomization using flame atomizer. So this is what the flame looks like. So it's a laminar to non-turbulent streamline flow. Only finest solution droplets reach the burner. So in the sample, you have an oxidant in the fuel that are mixed. So usually, if I'm not mistaken, the oxidant is the acetylene, and the fuel is the gas that we usually have. Okay. Now there's a one-to-one fuel oxidant or mixed fuel oxidant. However, it can be adjusted for optimum excitation and desired compound. So the different mix give different temperature from 1700 to 3150. Now it provides flame and a long path length. So used mostly for alkali metals like sodium and potassium. In AES, because they are easily excited even at low temperature. You can also use flame atomizer in AAS and AFS. Now the disadvantage is the temperature is not high enough to extend to many other elements. So if you have this flame atomizer, so this is how it looks like. Yeah. So your sample is usually aqueous sample drawn by passing a high pressure stream of compressed air past the end of the capillary tube immersed in the sample. And when the sample exits, the nebulizer strikes a glass impact bit which convert it into fine aerosol. So once the sample passes through the nebulizer, okay, it gets out of the nebulizer in the form of the aerosol. Okay, an aerosol means to a dry aerosol of small solid particles. Now the flame's thermal energy then volatilizes the particle, producing a vapor that consists of molecular species, ionic species, atom, and ionic species and atoms. Okay? And if you're going to look at the frame structure that you have here, the selection of the right region in the flame is important for the optimal atomization energy performance. You can look at the primary combustion region. So this is, we could say, the inner blue or the blue inner core. So the primary combustion zone or the blue inner core is not in thermal equilibrium and not used in spectroscopy. Now the interconal region is the region of the highest temperature. It's rich in free atoms, and this is the one that is used in spectroscopy. That's the one here. Okay. Now the outer core is a cooler region which is rich in oxygen due to the surrounding air, and that's where metal oxides are usually formed. So we'll discuss about this during our synchronous meeting. And then I want you to look at the video about atomization, the methods and the source, especially the flame. Okay. Now let's look at electrothermal, or the so-called graphite furnace. So graphite furnace AAS is, or electrothermal atomization, atomic absorption spectroscopy. So the atomization method that we have here, you have a small sample that is placed inside a graphite tube. Okay, so this is your graphite tube. So through an inlet using, the way you introduce is through an inlet using a microliter syringe with samples volume ranging from 0.5 to 100 microliter. So here the tube is heated electrically in 3 stages. So while it's being heated, the sample solvent is eliminated or evaporated. The sample is ash, and then the temperature increases rapidly to 2000 to 300 Kelvin to quickly vaporize and atomize the given sample. Okay, so you can look at the video here on how to set up and maintain a graphite furnace. And then we will discuss this during the synchronous meeting. Okay. Now let's go to the ICP. So in an inductively coupled plasma, the plasma is the electrically conducting gaseous mixture composed of cations and electrons, reaching 6,000 to 8,000 degrees Celsius. So that's just so high compared to the one that you have. That's 2 to 3 times higher than the other atomization method. Okay, so in ICP OES, you use high temperature plasma for sample ionization or excitation. You use higher fraction of atoms existing in the excited state, giving rise to an increase in emission signal and allowing more types of atoms to be detected. Now, if you're going to look at the mechanism here, okay, of this what we call ICP, so the ionization of the flowing argon is initialized by a spark from a Tesla coil. Okay, so the resulting ions and their associated electrons, they then interact with the fluctuating magnetic field produced by the coil. Now, this interaction causes the ions and the electrons within the coil to flow in the closed annular path. Okay. So to identify, to understand more about this, how plasma generated in ICP, you can look at this video. You can also look at the principles of the ICP here. It shows you the basic components of the ICP-MS and how sample is analyzed in the ICP-MS. Now, we can answer this question during our asynchronous session. Okay. Now, What are the methods for introducing your solution samples? So one that we have here is the so-called cold vapor generation. Now, why do you think this is needed? And specifically, why for mercury? Okay, so the cold vapor generation. So if you're going to look at the typical sample introduction, you heated them. So imagine if you heat mercury. So from a solution, it just become gas and you're around the instrument. So that's not really good. So what they do is they apply the so-called cold vapor generation. Okay, because it is only the metallic element that has an appreciable vapor pressure at ambient temperature. Remember, mercury is a liquid. So it's easy for it to become a gas. That's why it has an appreciable vapor pressure. So uses a special cell that does not require it to be put into the flame. That's why it's called cold vapor. So if you're going to look at this cold vapor process, usually it has something to do with hydride. So there's a sample of mercury decomposed in a hot mixture of nitric acid and sulfuric acid, followed by reduction with tin chloride. So if you're going to look at this, okay, so there's an air, there's a pump, so there's a reaction mixture with the sample containing the mercury, and then the water and the mercury vapor, okay? They will pass through the drying tube containing the triide, and then your mercury vapor, okay? You can collect it through the observation cell, and then passing through the quartz window with a mercury hollow cathode lamp, you can determine the sample. Okay, so the mercury, the elemental mercury is then swept through a long pass absorption tube by bubbling a stream of inert gas through the reaction mixture, and this determination is completed by measuring at 253.7 nanometer. Okay. Now, there's also another way wherein they use the so-called hydride generation. I think I mentioned that earlier. This is a method for introducing samples containing arsenic, antimony, tin, selenium, bismuth, and lead into an atomizer as a gas. No, the volatile hydrides can usually be generated by adding an acidified aqueous solution of the sample to a small volume of a 1% aqueous solution of sodium borohydride that is contained in a glass vessel. So the typical reaction that you have here, you have arsenic 3+, you have the sodium borohydride there, okay? And then you form ASH3 reacted with acid at high temperature, you produce arsenic and hydrogen. And if you're going to look at this, this is how hydride generations happen. So the hydrides generated must be heated in air and acetylene flame or electrically to create atoms in the free state. So a volatile hydride containing the sample is generated and carried to an absorption cell in the light path of an atomic absorption spectrometer. Okay, so you have a sample in the sodium borohydrate there. So there's an inert gas. So once your metal is produced, okay, from an ionic form to the metal, it just passed through there. So it's just for safety precaution, the way that they do it. So what are the possible interference in atomic spectroscopy? So there's two types of these atomic interferences. We could say spectral interferences It arises when the absorption or emission of an interfering species either overlaps or lies so close to the analyte absorption or emission that the monochromator cannot resolve them. So when the emission or absorption lines overlaps, separation is less than 0.1 angstrom. It's very rare, but still they can have an overlap. So the way that you can do is, let's say you have, I want to put a specific example here. So whenever you have aluminum and vanadium, so if you're going to look at the wavelength that they have, 3,992, or wait, 3,800, 3,082.15 angstrom for aluminum, and 3,082.15 angstrom. They're so close, right? So the way that you're going to solve this is use this wavelength. So what happened when you use this wavelength? When you use this wavelength to analyze your aluminum, any interference from vanadium is eliminated, or vanadium is eliminated. Okay? So that's what we call the spectral interferences. Now, the other one that we have here, we could say there are other spectral interferences that I'm going to mention as we go on. Okay, but if we're going to look at the other interferences, the other one is a chemical interferences. So it results from various chemical processes occurring during the atomization that alter the absorption characteristics of the analyte. So let's look at these spectral interferences one by one, and then chemical interferences. So we can have in a spectral interferences some sort of a correction method. So I mentioned to you before about this, what we call chopping, beam chopping. So open, close, open, close. So you can use that. You can have a rotating chopper, okay, that allow and then blocks the signal coming from the lamp to the burner. And if you have it, you can see it is open, close thing. So the problem that we can have is the flame in AA is that light from the flame and the light source both reach the detector. And the measurement is a really small signal from a large background. So how do we solve them? You subtract out the flames to get only the light source signal. The light that was transmitted over the incident light. So the lamp and flame emission reach the detector, and then only the flame emission reaches the detector. And it would result in a square wave signal. Another correction methods that we can have for spectral interferences is if we have a problem where molecular species may be present in flame. So we can use a background correction using the deuterium lamp. So the absorbance spectra overlap since molecular spectrum is much broader with a greater net absorbance. So you can use here, okay, some sort of deuterium lamp. So there's a deuterium lamp, your hollow cathode lamp. So if you're going to look at this, you pass through the electrochemical analyzer and you have there your monochromator. So you could see here calcium hydroxide emission. Okay, so the difference that we have there. So the absorbance from the hollow cathode lamp, so that's equal to the absorbance of both the atoms and the molecules. So what you do, you get a signal from the deuterium, you correct it, you subtract it from the overall signal from the hollow cathode lamp, and you can get the absorbance of the atom. So let's say this is the whole thing that you have. And with your deuterium lump, you could say, oh, half of them is this one. So the correction that you have there, that's just the atom. Okay. Now you can also do this so-called Seaman background correction. So this is just placing your gaseous atoms in magnetic field. It causes the random orientation of the atoms. So you have a gaseous atoms absorbance like this one, and then in the hollow cathode emission lamp, this is what you have. So the absorbance measured without magnetic field, and this is the hollow cathode emission. So if you're going to look at the with the what we call magnetic field, what will happen? The atomic energy levels is split by the magnetic field. So that one thing that you have there will become two. So the atomic transition has the wrong polarization to absorb the light from the lamp. So the absorbance measured with the magnetic field. So here you can going to look at it, the absorbance without the field and the one with the fields. And the difference is the absorbance of your analyte. Now you can also look at what we call the chemical interferences. So one thing here is the formation of compounds of low volatility. So they don't convert to gas form. So you have an ions and a cations, they give you salt. Okay. So you can have a calcium ions with sulfate ions to produce calcium sulfate salt. Now it's an interfering results, it decreasing the amount of the analyte that's atomized, and it decreases the absorbance of the signal. So there's what we call a negative errors. How can you avoid this? You increase the temperature of the flame, you increase the atom production, higher temperature. You can use the so-called releasing agent. So other atoms that bind with the interfering ions, like for calcium, they use strontium. So instead of calcium reacting with the sulfate, the strontium react with it. So it increases the calcium atom and the calcium absorbance. You can also add, we could say, protecting agent. Okay. So the protecting agents, they bind to the analyte, but they are still volatile. Like for instance, for calcium detection, you can release EDTA. So calcium plus EDTA, it gives you the calcium EDTA complex. And then that can be converted to calcium atom. And last but not the least, maybe you can do a method of standard addition. Okay. Now, another thing that we can look into chemical interferences is the so-called formation of hydroxides and oxides. It's going to have an interfering results. It's going to be non-volatile, okay, and intense molecular absorbance. And how do you prevent this? Increase the temperature of the flame, use less oxidant, and then use the method of standard addition. And then you have ionization. This is most prevalent if you use high temperature. Hotter ionization, atomization means more ionization emission from interferences. So most prevalent in high temperature because when there's substantial production of free electrons in the equilibrium, like what's happening here, so there's a lot of your M+. Okay. Now it would reduce the sensitivity of your analysis. So how do you correct there? You lower the temperature. You add this so-called ionization suppressor, creates a high concentration of the electron that suppress the M+ by shifting the equilibrium. So remember in your Gen Chem, you increase this one, the backward reaction is favored. So maybe you can add a metal that can be ionized more easily. So when you can ionize easily, you have there more electron. Okay. Now, the example that we can include here is we could say potassium. If you're going to look at the potassium, okay, the absorption and emission of the potassium to give you K. So if you're going to have, let's say, potassium ion that is being produced, there you can add cesium. So cesium would readily ionize in the flame because it is lower ionization energy than sodium. This is the analyte. So the shape of the equilibrium prevents the ionization of your sodium. So you can also use in your potassium. I think in our experiment in determination of calcium, we use also cesium. Okay, so this experiment exercise, we're going to discuss this on the synchronous meeting. And that's it for this module 4.3. Till the next module.